question into that. Okay, now for example, this half reaction versus this half reaction. So now you combine the two half reactions into a complete reaction. Okay, so looking at this one, this serum 4 plus is going to be a strong oxidizing agent, right? Because it has a high magnitude associated with the plus. So you're going to use, for example, serum 4 plus as oxidizing agent. So looking at the next one, then oxidizing agent, that means it's going to reduce your analyte. Okay, so looking at the two, so this is your half reaction written in a reduction form. And therefore, if you do analyte, then this is the analyte you're looking at. Cannot be that. Okay, you cannot, this is the highest oxidation state, then you cannot oxidize it further. Okay, so this becomes your analyte, then you can use the two chemicals, this chemical and that chemical. And therefore, you end up with this oxidizing agent. Your analyte will be this. Okay? Notice this is H3. Okay? So this whole deal is anion. So you end up with that. So losing the 3 plus, I made a mistake here, is the anion is a -3. Okay, this is -3. Okay, then when this whole deal is -3, the arsenic has to be a cation. Okay, it has to be a plus. So you can do the math. Okay, so there's a -6, -6. So it turns out the +3 is associated with the arsenic. It's a +3. Okay. Okay, so this is your E overall, right? So this stay in this position, and then this one switch as oxidation, then combine. So is equal to 1.7 minus 0.559, right? That's what the delta represents. Delta means minus, difference. Okay, so it's the larger one subtract the smaller one. So you end up with this, right? Plus meaning spontaneous, okay? Then the magnitude is quite high. Now, so this, if you predict this is a fast reaction, then you would be wrong, because experimentally, it is slow. It is very slow, okay? Then how do you know whether a particular reaction is going to be fast or slow? Then, we'll look at that next. Now, on the other hand, if the serum 4 plus titrate against Fe2 plus is a very fast reaction. Even the E overall, the delta E, is a lower magnitude. See, it's going to be a plus spontaneous lower magnitude than this, but this is a much faster reaction than this. Okay? So to set you up, to look at some the second limitation. Now that is the first limitation. We're going to answer that later. But look at the second limitation. Is here when you look at an electrode. So you have a conductor here, you have a solution here. Then you are talking about the redox chemicals. One is the oxidized form, one is the reduced form. In order for this to participate in the reaction accurately, so the quantity of this to the conductor, this quantity is measured accurately, then it must need to be reversible so that you can calculate according to that. So the difficulty is right here. So take note, because of this conductor could be oxidized. You operate the electrode in ambient condition. So there's a lot of air in your solution too. So that could oxidize the metal. So once you get oxide coating on it, then the reversibility will be reduced, right? So the oxide coating is going to prevent electron transfer. Now notice here, there's electron transfer, right? So 2 electron transfer in between the two, back and forth, back and forth. So if you have a coating, you're not going to have accurate electron transfer. So what it is now, if you have a coating, it becomes non-reversible. Okay, so as the oxide coating is thick, then there will be no electron transfer. So keep that in mind. There's a tremendous limitation in electrochemistry. Okay, one of the reasons electrochemistry is such a theoretical method. In theory, you can look at such low concentration. You can do single electron detection in theory. But then in practice, because of all these make it difficult. Then spectroscopy, that's why spectroscopy is superior in terms of practical application. But electrochem can get into something really hairy, physical chemistry type of calculations. So that's what's fascinating.
So
Jeffrey?
when you're detecting a single electron,
Oh,
is it the lowest possible energy that you've ever detected? So you just conclude that it's just one?
well, Faraday, right? Faraday number. You can incorporate into that kind of calculation here. Yeah, so single electron rather than 1 mole of electron, right? Avogadro's number. So you can treat that, in a half reaction, everything is 1 mole, right? 1 mole of electron, then you get this potential. So what about single electron? Then incorporate a 10 to the minus 23 into it, right? Avogadro's number instead of 1 mole. So 1 electron. Okay, so keep this in mind. Then come to, in practice, then truly reversible will be pretty much of these 2 metals. Okay, and this you don't want to mess around with, but still there's a mercury electrode for good application, in research. But then this is common, but silver is getting more expensive nowadays.
So those metals don't reverse, or they don't have the interference with
That's right.
oxidation.
Yeah,
Interference,
they have, they practically do not like oxygen. Okay, if you use lead and copper, those metals, they love oxygen, so will not be reversible. Okay. So in terms of reaction rates, right, analytical chemistry, then you analyze something, then you want to do titration, right? So of course you want the reaction to be fast. Then reactions, chemical reactions, are based on collisional theory, right? So you have 2 chemicals initially, then you end up with 2 different chemicals. So what it amounts to is that the 2 chemical looking at as a molecule, then they at a certain temperature, the activities, right? At a certain temperature, they will move. Then they carry kinetic energy and collide with each other. And there are other reasons too, energy as well as orientation and so on and so forth. Get right, then your reaction is fast. So once they collide, they form an activated complex. So this is energy containing, is being activated. you have kinetic energy dissipate, right? Dissipate into that. So if the energy is high enough that they will separate, break bonds and then combine to form two different chemicals. So it is the activation energy that is important to govern for the final product. So the key question is, whether you have enough energy here. So the activation energy explains. Okay, and the excess energy then go to the surrounding. So looking at that as a diagram,